video is an introduction to a very quantum mechanical, extremely surprising, at least from a classical physics perspective, property of electrons. So when you think of a little electron, right, it's this little particle. Actually, I should put a little minus sign carefully, so I'll put minus E. So this little particle, like, this is our classical conception of it. And we are learning that actually there is something vague about, say, its location, and also something vague about its, say, momentum. I'm not really sure how to indicate momentum vagary, but maybe I'll just put, a fuzzy arrow. But something that we're not vague about is the charge of an electron. The charge of an electron, right? So if Q represents the charge of this electron, it's got a very particular value. It's minus E, where E is that fundamental charge, 1.6 roughly times 10 to the minus 19 coulombs, right? Another thing that we're not vague about, so in a rough manner of speaking, we know the mass of the electron, right? So the mass is some, 10 to the minus 31 kilograms or whatever it is, but it's one of the properties of an electron, right? So if we are listing out all of the properties and qualities of an electron, right, we'll have no trouble saying what its electric charge is, and we'll have no trouble claiming a certain rest mass, right, rest mass for the electron. It turns out that this is not all you can say about an electron. It turns out electrons also have spin. And it's interesting, there is a spin quantum number equal to a half, and associated with this spin quantum number is an angular momentum that I'll just say, let's say it's called, it's weird because it depends on what book you look at. So I guess what people do is they say that the angular momentum is of an electron is designated by a capital S vector, and capital S vector has a magnitude equal to, it's got to do with this angular momentum quantum number for electrons. It's S times S plus 1, just like you remember seeing from atomic orbital angular momentum, except for S for the electron is 1/2. And the idea here is, so for example, right, for the electron, you put in 1/2 times 3/2, that's the square root of 3/2 h bar. So this capital S value is root 3/2 h bar, and that's another property of electrons. So the mass of the electron is like 10 to the minus 31 kilograms, and the spin of the electron is equal to, right, this is the orbital angular momentum of an electron, it's root 3/2 h bar, and no other value ever. So this is very strange. This swirl is permanent. I may have misspelled permanent. That's the thing about handwriting everything. I think because there's no spell check on handwriting. So permanent. Maybe that's, nope, that looks worse. So I'm sorry that this is a waste of your time. So I think this is the correct spelling. But this swirl is permanent. as in there's no way to get rid of it. You can't get rid of it. You can't change it. You can't increase it. Right? It's just like whenever you talk about an electron, you cannot change the charge. And when you talk about an electron, you cannot change the rest mass. Those are fixed values, right? It's a fixed electron property. So this is very strange. It's extremely quantum mechanical. It is unexpected. It's an unexpected, there is no classical reason for this property to exist. And this is incredibly interesting for an electron. But this tends to be, it seems to be nature's truth, right? Nature's truth is that these particles, electrons, are spin half and they have permanent angular momentum. So notice that we're talking about the magnitude of this type of angular momentum. But that means, right, that this angular momentum vector, it's sort of similar to the picture that I drew you in a previous video for the orbital angular momentum of an atom. If you draw, this is the z component of the angular momentum. We know that the angular momentum must be this length, but the z component can only ever be measured to be half h bar in magnitude. So the z component is either plus half h bar or negative half of h bar. So these are actually, all of a sudden we can talk about the z component of the electron spin angular momentum. And it's called m sub s. And m sub s can take values of, right? Do you remember the list? It goes like plus or minus L, plus or minus L minus 1, comma, all the way down to 0, right? Those are the m sub s values. But here, L is equal to 1/2, right? Because this is also known as the spin quantum number S. And so that means that m sub s can only take values of plus or minus 1/2, and then you actually skip 0, right? Because it's either plus 1/2 and you go right over 0 to negative 1/2, and you can't have m sub s equals to 0. So here are the z component of spin angular momentum, and this is the magnitude of spin angular momentum right here. Okay, so it's not like I can derive this property for you. And that honestly is very similar to nobody being able to derive the charge of the electron, right? Nobody can derive for you why the mass of the electron is its particular value times 10 to the minus 31 kilograms, right? These are properties that you have to discover, you have to measure, right? You have to realize exist and then develop an experiment to go measure it. So, yeah. So this is very, very interesting. All right. So one last comment is because the electron is charged, if electrons have spin, then this means electrons have magnetic dipole moments. And the magnetic dipole moment of an electron can be written down the following way. It's equal to, it's actually dependent upon the angular momentum vector, this thing right here, and it's equal to, it's dependent upon the angular momentum vector, and this equal sign is sloppy, so let me erase it. So it turns out that the value, although I'm not telling you why, right, but you can go read about why. So it's the electron charge divided by the mass of the electron, right? And you multiply by the angular momentum vector. And I'm tempted, actually, so in my notes, there's no minus sign, but I believe there must be a minus sign. So let me think about this. Actually, I'm going to pause the video and do some research real quick. Sorry, I'm back. Yeah, so I think there needs to be a minus sign. So I'm going to put it there and erase my question mark. So this is the definition, or it's the relationship that gives me how the orbital, how the orbital angular momentum associated with the spin or swirl of an electron, just an electron all by itself, not necessarily an electron in orbit, but because the electron has this frozen in spinning, it's got automatically a magnetism. It's a magnetic dipole moment. And this is the magnetic dipole moment of the electron strictly due to this spin quality. And there's a relative minus sign, right? So S actually is a material swirl, right? It's an angular momentum swirl, which is mass in motion around some axis. So it's not got anything to do with charge. But because the electron is charged, right, it's charged matter, and that charged matter is swirling, there is also a magnetic dipole moment associated with the electron. This thing right here. Okay? And S sub z is equal to the spin quantum number m sub s times h bar, like that. So we can also write that the z component of the angular momentum vector is equal to minus e over the mass of the electron, so the charge of the electron over the mass of the electron, times s sub z, which is m sub s h bar, where m sub s can be plus or minus 1/2, right? So this is the z component of the angular momentum, the z component of the magnetic dipole moment of an electron. All right, so okay, good. So there's one last small piece of definition, and it's kind of historical, but there's this, it's actually kind of a cool word. It's called the Bohr Magneton. So the Bohr Magneton is given a symbol mu sub capital B, and mu sub capital B has the value of the charge of the electron divided by twice the mass of the electron. And so if you look at what mu sub z can be, right, this is the z component of the magnetic dipole moment of our little spinning electrons, right? M sub s can be plus or minus half an h bar. So mu sub z can be plus or minus, right? This is, yes, the Bohr Magneton, yeah, excludes the h bar. It's, so it's, so this is sort of a historical way to understand the magnetic dipole moment, or the z component of the spin of an electron, based on this sort of like combined quantity. It's the charge over the mass of the electron, but with this extra factor of 2. It's called the Bohr Magneton. And it's, yeah, mu sub capital B. Okay, so in a following video, I'm going to describe the physical relevance, right, of the spin and the magnetic dipole moment. So physical, right, we should notice, we should be able to measure and experiment with these issues. And you'll see that these issues give rise to an interesting energy spectrum splitting, right? And so the following video, I'm going to describe this. So far, honestly, I've just sort of like claimed that there is this thing called electron spin, and then sort of defined some things around it, and then said if there is an electron spin, then that means that the electron is a magnet, right? And because of the space quantization of electron spin, you have a quantization of the magnetism, or the magnetic dipole moment's orientation and size. I also defined this quantity called the Bohr Magneton, so you could give it a 3-bar equal sign. It's a definition. It's just a sort of a convenience. Yeah, and we wrote the magnetic dipole moment in terms of that Bohr Magneton. So the next step is to ask, why is it important? Like, how do we know that this is nature's truth, right? So that's, yeah, that's the next video.